Welcome to Maths with EJD. In this video, I still continue with linear programming, and here we are looking at special cases in graphical solutions. We've already considered two special cases before now, you know, special cases. Two had been considered before now, and the first was the multiple optimal solution case, multiple optimal solutions considered already. Then we also considered infeasible solutions. So in that case, you have no possibility of solutions. And here now we are looking at unbounded solutions. Unbounded solutions. Okay. So let's see what this is about. So in the case of multiple optimal solutions, right, we talked about the possibility of having two or more optimal solutions, giving us the same maximum or minimum value of the objective function. An infeasible solution, no solution at all. Now, talking about unbounded solutions, let's see what that is. Unbounded solutions. Okay. Now, unbounded solutions in linear programming, or LP for short, unbounded solutions in linear programming occur when the feasible region, when the feasible region does not restrict the objective function, does not restrict the objective function from increasing indefinitely. This situation arises when, number one, there are directions. There are directions in which we can move infinitely, while still satisfying the problem's constraints. Okay, that's one. Another one would be that the objective function the objective function can take on arbitrarily large or arbitrarily small values, leading to a lack of a maximum or minimum value. Okay. So in other words, an LP problem has unbounded solutions if there is no upper limit, on the value of the objective function within the feasible region. Okay, so that's how it goes. Now, let's take an example to demonstrate this, to drive the point home. So here we want to maximize z equals 2x plus y subject to the constraints, subject to x minus y is less than or equal to 1, and x plus y is greater than or equal to 5, as well as the non-negativity constraints as usual. All right, we already know the standard procedure for solving this. So you're going to get line 1 from this, you're going to get line 2 from this, and let's see what that brings. So line 1, for instance, is x minus y is less than or equal to 1. So here it becomes x minus y equals 1. And that means that at x equals 0, then when x is 0, right, you have minus y equals 1, which implies that y is equal to minus 1. Okay, so in that case, you have 0 and minus 1. Then, still on line 1, right? So at y equals 0, okay, when you set y to 0, so y is 0. So that means that x is simply 1, so that there you have 1, comma 0. Okay, so you need 0 minus 1, 1, 0 for to plot the point later, to plot the to draw the line, so to speak. So L2 now is x plus y is greater than or equal to 5. But as a line, it is just x plus y equals 5. So again at x equals 0, y is equal to 5. Then at y equals 0, x is equal to 5. So here you have 0, 5, and here you have 5, 0. Okay, so we can go for the plot now. We can go for the line. So the biggest value on any side is 5, right? So we can have this. So this is x. It's 1, 2, 3, 4, 5, and maybe 6. Origin, 1, 2, 3, 4, 5, 6. That's y-axis. So for line one is 0 minus 1, 1, 0. 0 minus 1, 0 minus 1, 1, 0. So that's x is 0, y is minus 1. So it means we need minus 1 around here. So x is 0, y is minus 1. So that is this point now. Then on the other hand, we need 1, 0. Okay. When x is 1, y is 0, that's just this. So now what we need to do is to join the 2 points and project it for as much as we can. So take it as far as you can take it. Then look at the sign. It is x minus y less than or equal to 1. So, this is 1. Now, if you want something less than 1, it has to be at the upside of this line, because at the downside, it means you are going to be talking about greater than 1. But we are talking about less than or equal to 1. So we keep shading in this direction like this. Okay. Now, of course, because of space, I should still keep shading all this all the way down, but I don't want to cover up those things. So we have that, right? The next thing we want to do is to, okay, so now this is line 1 clearly. Then for line 2 now we have 0, 5, 5, 0. That's simply 0. This is 0, 5, x is 0, y is 5. Here x is 5, y is 0. So you also join the 2 points together, okay, and project it on both sides. Then look at the sign. The sign is x plus y greater than or equal to 5. So greater than or equal to 5 also means you shade the upper part, okay? You shade the upper part like this, the upper part this way. So now any region where green and orange intersect, that's the region you want. So that's like this region now. So all this region, okay? You have this region. So you see all this region like that. So, but the interesting thing is that the lines, you can keep projecting the line forever and ever, and it will never end. That's the thing about unbounded solutions. So, you can still take this line, you can keep projecting this line and keep projecting this one. But I mean, I probably let me create space So you can really get the gist of what I'm trying to do. Those numbers up there are really stopping me from doing everything I should do. So I think I'll take the pain to just do to show what I really mean. Okay, let me bring it down so that it can be it can be clear, it can be as clear as possible. Right. Yeah. So again, permit me to draw the line again. So now I have this and I have this. In fact, let me let me draw it forever if possible. Okay, now this is y and then this is 0, right? So, and then we have 1, 2, 3, 4, 5, 6 for the x-axis. And for the y-axis, we have 1, 2, 3, 4, 4, 5, and 6. And because I saw a -1 somewhere for on the y-axis, so I can project this down a bit, and I know this is -1. So we go again. So for line one, I need 0 minus 1, 1, 0. So 0 minus 1 means x is 0, y is -1. So this is this point now. Then I also have 1, 0. That is x is 1, y is 0. So this is this point now. So then I can join the 2 points together with a straight line and keep projecting it for as much as possible. Okay? Keep projecting it as much as you have space. So, okay. Keep projecting it as much as you have space. So, okay, I can stop here. Now, what's the direction for that? X minus y is less than or equal to 1. So if you less than or equal to 1 will be, so this is 1 now, for instance. So if you want it greater than or equal to 1, you go down. But if you want less than or equal to 1, you have to go up this direction. So that is where you have less than or equal to 1. That direction like that, less than or equal to 1, like this. Okay, less than or equal to 1. Now, there's actually another approach where you shade the region that is not required. Okay, but here I'm shading the required region. So I think shading the unrequired region actually helps so that the point of intersection will end up being that point that is not touched at all. So, but here we've chosen this idea of shading the required region, so it's fine. So just choose your style and stick with it. Now the second line, okay, now this is line 1. This is line 1. So for line 2 now, which I'm going to do in green, line 2, that's 0550. Okay, so this is 0, 5, x is 0, y is 5, and 5, 0, x is 5, y is 0. So we can also join the 2 points together. No, that's not perfect, but at least we know what we're talking about. So the other part, so that is now x plus 5. I mean, x plus y is greater than or equal to 5. So greater than, of course, we know this is 5 now. So below the line, you're talking about less than 5, but greater than 5 will be at the top. Okay. So again, project as much as possible. Okay. So above that line, from that line upwards, because it's less than, greater than or equal to rather. So greater than or equal to, like that. So, but you see, the issue now is the region you need is actually where orange line and green line intersect. So, and then they have a boundary. So this is like the boundary now. L1. Okay. So this is this L1. This is the boundary along this side. Okay. And for this other side, this is the green line is the boundary. Yeah. Okay. So you see everything in between the two lines like this now. That's the region you require. This is the region you're interested in. Is this the bigger one? Yeah. I think this makes things faster. So now you see this is the region you are interested in. So now you see that the region keeps going endlessly, just keeps going like that. There's no end to it. So you can keep going as much as possible. In fact, it still keeps going like this. So if as far as you can keep drawing the two lines, it keeps going. So you see the feasible region, solutions exist, but the solutions are infinitely many. So it's not there, no boundary. You can, as far as you can keep, you have space to draw the lines. The region keeps going like that. And that is why it is called unbounded solutions. Okay. So you see, okay, I did not indicate line two. So this is the green line is line two. So this is line one and line. So it's like you have that the two of them intersecting, and then there's so it's the mouth is open so much that it's going all the way up. So one way to also demonstrate this properly is to use Desmos, which I've been using quite a bit. So let's go to Desmos. So you can see this. This is so you can see the solution where the solution lies, right? It's unbounded. Let me do that. Okay. Yeah. So we have unbounded solutions lie in this region. So the feasibility region is so large that you cannot see the end of it. That's why you call the solutions unbounded in all that yellow region. Okay. So let's go for Desmos to see, to also have a clearer view of what this looks like. So then we'll plot the lines. Line one is x minus y less than or equal to 1. So you see that. Then line two is x plus y is now greater than or equal to 5. Okay. So now you see the where the both of them intersect is that, so you can see it's like that that funnel, so to speak. So you have, so you see you can keep going forever and ever, and it can go to 1 million, and it's still, the region is still that overlapping one. Okay, that overlapping region. So that's why we say it is unbounded. We have unbounded solutions. Okay. So here, maybe if I could use the same color I did the other time. This is okay. Let me see if I can change the color. Is it possible? I think it's possible. I've tried it before. I think it's not working here. Okay. Somehow it's possible normally. So all right, so you see that point of intersection and it goes on forever and ever. So whether you go to the right or to the left, it keeps going. So that's why you say the solution is unbounded. Solution is unbounded. Okay, so that brings us to the end of this video about the special cases in graphical solutions for linear programming problems. So where we have seen I mean, two videos before now, I think we talked about multiple optimal solutions, and then the video before this we talked about infeasible solution where there are no solutions at all. Now we have talked about unbounded solutions. So the solution is it just keeps going forever and ever, no end to it. So if you have not subscribed to this channel, be sure to do that. Then hit the notification bell also so you can always get alerted each time a new video is released. Don't forget to comment. Tell me if you need me to teach a topic or solve a problem. And then also like and share so that more people can have access to all this great learning. Till I come your way again, keep optimizing. Bye.